mouse off of that, it'll like expand all the way and type it in your thing. Like, just like move it in the middle somewhere. Because I know there's like a display mode where it'll type it in. Yeah. And it's just display mode.
Bottom corner.
Bottom right corner?
Yeah,
Oh, okay.
Yeah, that way it cuts those bars out.
Where's my mouse? Yeah, what did I do? Okay, where's my mouse? Okay. Okay. It's challenging my orientation abilities.
Oh, perfect. Oh.
Okay, so
Maybe no.
we'll try to adjust with that. Okay. So let's do this example here. Okay. So a bag. In general, this is if in probability problems you will see this as urns, like EURN, but whatever, it's a bag, right? Contains 5 red balls and 2 green balls. Okay, and then 2 balls are drawn. One after the other. What is the probability that the second ball is red? That's what I want you guys to calculate. Without replacement, that's correct. I'll give you guys 2 minutes. I would encourage you guys to work in groups, and hopefully after 2 minutes I'll have a volunteer. Yes.
Alright, so you're now to that area. What do you do total?
So I bet he's doing 5 red balls and 2 green balls, 2 golden balls. This might be the second one.
Yeah. So then what like?
Oh. Travis, you're looking to
Yes,
art and data writing for nice science.
So I would recommend using the law of total probability to solve this. Recommend using the law of total probability to solve this.
So there's different balls, right? So you first you get red balls, you get was a conditional probability. Where's you get there? Because if I pick up a red ball much this morning, that means that increases, it lowers the chance the probability of giving you another red ball.
So I can write this as probability of R1 times probability of R2 given R1. Right?
Like the summation.
Yep. Plus probability of G1 given probability of R2 given G1. Right? And that's what Tito was calculating over there. So probability of R1 is 5/7 times probability of R2 given R1 is 4/6. Right? Plus probability of G1 is 2/7 times probability of R2 given G1 is 5/6. Everybody with me? Right? And this will turn out to be 7 times 6 in the denominator. We have 20 plus 10 on the numerator. We get 5/7. Now here's a slightly, another argument which can get you the same thing, but it's somewhat subtle. It's first. Let me ask you this question: does every ball has, if you identify each ball with its own name, does every ball has equally likely to be picked as a second ball? Right? Every ball is equally likely to be picked as a second ball, right? Because we're not doing any partiality, right? So that means since there are 5 red balls, the probability that the second ball is red would be 5/7. Right? That's how we confirm that there's another way of calculating the same thing. So in this example, every ball is equally likely to be picked as a second ball. Right? So now we will do another example where every ball is not equally likely to be picked as a second ball because something changes after the first term. Okay, so we'll do that. So hopefully this time our calculations will be faster. Question? Yeah, Sandra.
So the whole 5 sevenths in the end, is it just a coincidence that that's the probability in general of drawing of everyone, or?
Right, that's the argument which we just made, right? We are saying for the every ball is equally likely to be picked as a second ball. So if you just go through that argument, you will get, you will calculate the probability of second ball being red is 5/7 because there are 5 red balls and total 7 balls.
So it'll always.
Right, in this example, yes, but then we'll do another example where that's not the case. Okay, because in this example that is the case because every ball is equally likely to be picked as a second ball. But if something changes after the first ball, that won't be the case. Okay, and
every ball is equally as likely to get chosen.
Right, as a second ball. Every ball is just as likely to be chosen as the first ball. Every ball is just as likely to be chosen as the second ball.
Oh, every ball individual, including
Right.
each individual.
Right, not a color ball, but every individual ball.
Okay.
Okay. So now let's do another example. Again, we are starting with the same urn or the same bag, right? So we have 5 red balls, 2 green balls. Okay, you draw a ball. Let's see. Now, if green, you add a red ball. Okay, and then if red, you add a green ball. Okay, and then you draw another ball. Everybody clear with what's happening here? There are 5 to begin with. There are 5 red and 2 green. You draw a ball. If what you drew was green, you add a red ball in. If what you drew was red, you add a green ball in. After you do that, you draw another ball. Now what is the probability of having the second ball as red? See, now not every ball is equally likely to be picked as a second ball, right? Because something is happening after the first ball.
I'm assuming it's still without a place
replacement, you're just adding.
Right, but you're not replacing the same ball, you're replacing a different ball. Look at statistical independence. Independence is probably one of the most important properties of random events, and one of the most difficult to verify in reality. Right. So before we begin, let's say if you're gathering some data from multiple sources, right? So let's say if you hear about certain news from several different news stations. Now the real question is, are you getting independent information from multiple sources, or maybe all of them have the same source, right? In which case it's not really independent sources, right? So in general, in reality, figuring out whether two events or some information or something happening is independent of each other is very difficult to do. But fortunately for us in communication systems, let's say when I say I transmit one bit and then I transmit another bit, it's a very simple say assumption to make that the probability of one bit getting flipped is independent of the other, right? Because what's happening in the transmission in the wireless medium to the one bit does not necessarily affect the other bit. Sometimes it does, and we'll see how to handle that, but most of the time we'll assume that the bits getting flipped are independent of each other.
We'll probably get to this later, but what about if you miss a bit or something like that? If you miss a bit, it's not flipped, but it's just not there.
So right, we have to, first of all, we have to figure out that it was not there, right?
Exactly.
So maybe the question is, what you're getting is just a noise, or the transmitter stopped, right? So, and then usually there are several protocols on to say, okay, maybe at the beginning of the transmission you'll say, I'm going to transmit 30 bits, and then you only receive 29, maybe something got lost, right? Or every so seconds I'll send one bit, right? And then you think you receive something for 31 seconds. So that means there was something, there was a pause somewhere in between there, things like that. But it depends on the particular technology and what kind of protocol they're using and so on. But anyway, so by definition of the independence is actually pretty straightforward. If the two events A and B, then we will say that A is independent of B if probability of A given B is equal to probability of of A. That means if I tell you B happened, that will give you almost no information about A, right? Or in fact, that will tell you no information about A. Your estimation of A happening is completely unchanged by you knowing that B happened. Okay. So let's look at some examples. By definition, that's pretty simple, right? Okay. So let's say there's an experiment where you toss a coin twice. Okay. So how many outcomes are possible? 4, right? Okay. Then consider these two events. H1, which is the event that the first toss is heads, and T2, the event that the second toss is tails. Are these two events independent? Right? Because the first time you toss it, that has nothing to do with the second time you toss it, right? Okay, so that means probability, what you say is probability of H1 given T2 will be equal to probability of H1. Similarly, you can also say probability of T2 given H1 is equal to probability of T2. right? Because so H1 and T2 are independent events. Now let's verify this just to get our hands dirty with this conditional probabilities. Let's verify this in a much roundabout way. So what I want to do is calculate P of T2 given H1 as P of T2 intersection H1 divided by probability of H1. Right? So since all outcomes are equally likely, then I just have to count the number of elements in this set divided by the number of elements in this set. Right? So let's see. So all the outcomes are tails, tails, heads, tails, tails, heads, and heads, heads. How many elements are in T2 intersection H1?
Yeah.
One, right? Because what this says is second toss is tails and the first toss is heads. So there's only one outcome that is in that set. How many elements are in here? 2. So that's half. Right? Okay. So now what is P of T2? P of T2 will be equal to so basically the number of events or the number of outcomes which satisfy T2 divided by the total number of outcomes. Right? Number of outcomes which satisfy T2 are let's say this is first, this is second, so 2. Total number of outcomes are 4. So this is also half. Okay. So when that happens, these two events are independent. Good. Okay. Any questions about statistical independence? All right. So finally, we'll do. Finally, but it's already 11:40.
I feel like I'm in high school again. I feel like I'm in high school again.
I don't know why we do it this way.
No.
50 minutes, really?
It didn't have to go by this fast though. Usually it's like.
Yeah. They just try to
Maybe now that
schedule
we're
everything like, I remember last
Yeah.
semester just scheduling just that stuff. So
Okay.
they're just trying to
Longer.
fix it so everyone's
Yeah.
happy.
So okay, so this is you use Bayes theorem to usually invert conditional probabilities. So this is what we mean by that. Say, and then we're just going to derive it here. Okay, and it's not technically a complete derivation because there are some caveats which we'll have to take care of, but we'll ignore certain points. Okay, so this is like a rough sketch of the derivation. So let's say A intersection B is equal to P of A times P of B given A. Everybody agree with that? That's the definition of a conditional probability, right? Also will be equal to P of B times P of A given B. Okay? Alright. So now if you look at this part of the equation here, then I can say P of B given A is equal to P of B times P of A given B divided by P of A. Okay, so what this means is if you know the probabilities of individual events and if you know the probability of A given B, that means you can calculate the probability of B given A. So that's what I meant by inverting conditional probabilities. If you know one event condition and another, you can calculate the probability of the other condition on this event. Okay, and then it follows straight from here. The slight caveats are, what happens when one of these probabilities are zeros, and that's why those are the subtle points which I'm glossing over. Okay, but that's pretty much how you get that. If you don't remember this, just try to use these formulas to get here. It will be straightforward. Okay, so that's the Bayes theorem. And again, like independence, on face it looks pretty simple, but you can when you convert that into logic, you can there can be very bizarre scenarios over there, right? So basically in logic, you're saying, given that you know information about A, how does that change your information about B? That is very different that given that B, you know about B, what does it change about A? That two situations can be very different. That means this probability can be very different than this probability. Okay, so now we'll do next example. We have 10 minutes, so we can do it. All right. So this is a case where, all right, let's say there is a disease, right?
Okay.
Damn it, right? It's a dangerous disease, but only 0.5% of population have it.
My disease is affected.
Right? That means the probability is 0.005. Right? And this is called the base rate. All right. So somebody, there's a big drug company which develops a test. Okay. So they're saying, okay, if you undergo this test, like a scan or something, then they can tell you if you have that disease or not. Okay, but they won't be right 100% of the time. So they give you some statistics, right? So and this is what they tell you. So test is highly accurate with a 5% false positive. All right. So let's say disease D plus is the event that you actually have the disease. D minus is the event that you don't have the disease. Okay. And then T plus is the event where the test tells you that you have a disease. T minus is the event where the test tells you that you don't have a disease. Okay, so these are test results. These are reality. Okay, so now accurate with 5% false positive. So that means probability that the test tells you have a disease, given that you don't have a disease, is equal to 0.05. Right? This is called false positive. That means you don't have a disease, but the test tells you that you do. Okay, and then probability that the test tells you don't have a disease, but you actually do, is 0.1%. Okay, so this is false negative. Right? False negative, that means the test is telling you that you don't have a disease, but you actually have it. No, these are numbers. This is like 10%, 5%.
Is that a T minus on the bottom one?
Yes, T minus. T minus. Okay. So if you look at these numbers, would you say this is a good test? Why not? It seems like, you know, in this case it's like 95% accurate, right? In this case it's 90% accurate. So 95% and 90%, don't you think it's a good test? Why not? So you're talking from a moral perspective, right? So from accuracy, do you think it's accurate?
It's accurate.
It's accurate. Okay. So now let's calculate this. What is the probability
I guess we're really biased.
that you actually have the disease, given that the test tells you have a disease?
That it does.
What is probability that you actually have the disease, given that the test tells you that you have a disease? What is that probability? Means you go to the doctor, they'll do a scan, and they're telling you that you have this disease. Okay, but what is actual, given that they told you that, what is the probability that you actually have it?
Would be the percentage of the population that actually has it.
That is 0.005.
Yeah, that multiplied by the percentage chance that it is accurate, which is 95%.
Oh, you're telling me the answer? Yeah, so what this means is probability of D plus is equal to 0.005. That's the base rate, right? That means the probability of D minus is 0.995. You wanna?
The notation, do you have to make like, if we're gonna do that false positive, but do the complement of that? So that's like the right notation to do it, right? If we're gonna use 95 instead of the 0.05?
Right, so if the probability that T minus given D minus will be 0.95.
So if I want to do the complement of that, how would
Right, I want
notate
you to
that?
calculate this. So do whatever you want, calculate this.
But not the notations yet.
What?
You see what I'm saying? Like I want to write the notations out to solve it, if that makes sense, what we've been doing. But I want to use the complement of the T plus whenever D minus happens. So how do I write that?
So you just complement of T plus is T minus.
I guess I don't know what I'm saying.
What's new?
I'm using the I'm using the 0.95, not the 0.05. See what I'm
Okay,
saying?
yeah, so if you use, that means that what you're writing is probability of T minus given D minus is 0.95.
Okay.
I guess I don't understand your question.
I'm just as confused. I don't know what I'm
Are
saying.
you trying
Do
to
you want,
see
are you
what
trying to
is
ask the true?
0.95?
Do you see
What
what I'm
is?
saying?
I'm trying to say what is 0.95?
Because if you're trying to find the positive, he gave me the false negative.
What's positive?
So it's 0.05.
So you're
So-
asking,
So I want to use a 0.95.
now you're trying to ask what
Since
is
we are running out
0.95?
of time, maybe I'll give you a hint and then we'll see if you want to continue. Okay. So again, we'll just use the condition, the definition of, you just use the base theorem, right? Because we all know these conditional probabilities. All we need to do is revert them. So in order to do that, I know I have to do P of, let's say, D plus intersection T plus given P of T plus. That's what I need to do. Right? So this will be equal to probability of, but I know what is T plus given D plus. Right? So this means probability of D plus times probability of T plus given D plus given by probability of T plus. Okay? Probability of T plus given D plus would be 0.9. I know what is probability of D plus. All I need to do is calculate probability of T plus. How would I do that?
T plus,
Uh-huh.
that is the probability you actually have
No, that is a probability that the test will tell you that you have a disease.
95%.
Brent.
Yeah, I was going to say it's like 1 minus 0.05 because take the complement. of-
No, so 1 minus 0.05 here. Will that be probability of T plus?
Should be.
Why?
Because
So let's see, what you guys are saying is
within the
probability of T plus will be equal to 1 minus probability of T plus given D minus.
Yeah.
Right.
wouldn't it just be, there's either two possibilities. If you're given the test, there's either a 0.05% chance that it was wrong or a 95% chance that it was right.
No, not given a test. Assuming that you don't have the disease, then there is a 95% chance that the test will tell you you don't have the disease. That's what that means. Right, given D minus, right?
Oh. Oh, that's what that was.
0.005 is the probability that you actually have the disease. So 0.995 will be probability that you don't have the disease. Right?
Oh,
So there are two things. Whether you have the disease or not, and whether the test is telling you whether you have or not. There are two different things.
okay, so you would need to multiply the 0.005 times the
Right. So what Brent is getting at here is, if you want to calculate P of t plus, what you want to do is P of t plus will be equal to probability of d plus times probability of t plus given d plus probability of d minus times probability of t plus given d minus. Okay, so what are we using when you're calculating this? Huh?
Total probability.
Law of total probability. That's what we're using. And we know these conditional probabilities. And we know what these are. Right? So this will be 0.005 times probability of t plus given d plus would be equal to 0.9 plus probability of d minus will be 0.995 times probability of t plus given d minus is 0.05. Everybody with me? How much will this come out to be?
Wait, wasn't the T plus, I mean, with D minus is about 0.1?
T plus given d minus is 0.05. 0.05. And t minus given d plus is 0.1.
Okay.
Right? So t plus given d plus is 0.9. How much is this?
0.0543.
Okay. So now let's calculate probability of d plus given t plus. Okay, so this will be equal to I'm using this formula now. 0.005 times probability of t plus given d plus would be 0.9 divided by 0.0543. How much will that come out to be? 0.083. Right? So that means 8.3% if you want to talk in percentages. So in this case, if the test tells you that you have a disease, there's an 8% chance that you actually have it. Right? But at the outside it looked very accurate, right?
Wait, can you move up the paper? Like this one? Alright.
Okay? Yeah.
The 0.9, that came from the complement of false negative, is that right?
That's right. Because, yeah, false negative means true negative. Opposite of false negative is true positive.
Where did you get the probability for T plus given T plus?
1 minus t minus given d plus. So when you go back home, ponder about this, why is that such a big difference between these conditional probabilities? Right? It's very interesting reasons.
Everybody have a good weekend.
Maybe you'll have a
Happy birthday, Kyle.
Happy birthday, Kyle.
I don't know. I don't know about
Just to make sure I understood,
exactly.
for the T plus, we just use the total law of probability to sum up all the, I guess, conditions, because
Boy, I gotta get you an example. I gotta get you an
it makes sense.
I gotta get you
Is it sad that all this is just now making sense? I mean, no offense to AJ, but I'm not a PowerPoint professor, so this is all like just now. I took last semester, and it's just like, here's the formulas. I'm like, what in the hell? Now, like, literally all this makes sense. It makes it's easy.
The probability that the test tells you that you have a disease is the probability that you don't have it, and that it tells you yes, and the probability that you have it and it tells you yes.
Okay. I'm gonna go ponder on that.
Yeah.